the idea was that we have two sorted lists given to us, and we are going to merge, right? Like we do in a merge sort, for example. And we took each list and broke it into log n size blocks. Okay. Log n, yes. LLG is log n. Log n size block, and there were n over log n of such blocks. All right. And we take one element from each block. Okay. From one list, and similarly one element from each block from the other list. And now we've got a smaller set, and we are going to merge these two. Merging these two using the previous algorithm. Okay, whatever it was. The previous algorithm was fast, but didn't give you the best work, which is linear. Okay. Now the work for this will be linear because we are only, what was the work? N log n. Right? Now the work is the size of the set has become n over log n. So it is that log of that. So it's n over log n times log of n over log n, which is the same thing as n. So far, just to merge this using the previous algorithm, you can do this in log n time. You can do it in order n work. Okay, and that is our goal, to keep it fast and remain within the budget of order n for our work. Okay, but we've only merged these two lists, right? I've found the rank of every dot on the top list in the second dot list, and the rank of every dot in the bottom list in the top dot list. Okay, it's as if the real two arrays don't even exist for this purpose so far. Okay, now I am going to take the next step where I want to find the rank of every dot in the full list. Okay, so how do I find the rank of that dot? I know the rank of that dot, the one shown in red arrow, in the other dot list. Okay, which means it lies between those two dots in the other dot list. Now those two dots tell me where it might lie in the main list, right? Which is of size log n. So even if I spend a sequential amount of time, one processor doing all the work, I can in log n extra time tell the position of that dot from where this arrow began in the full array. Okay, how many such dots are there? N over log n, right? If everybody takes log n time, then work is order n and time is log n. Right? Similarly for the other side. Okay. So now we have found its position in the full array somewhere. We can find the position of every element in that dot list, top dot list, using so far only order n work, order log n time. And again, the other side. Every dot in the second list, we can find its position in the full first list in log n time, order n work. Same way. Right? Now what remains to be done? I only know the ranks, ultimate ranks, final ranks of all the dots. I only know the dots ranks. Okay. Now what about all of these elements that are between those two consecutive dots? I don't know their ranks. Right? But I know the ranks of the two endpoints. So we know those two positions in the full second list. So we know that all of these, the blue elements, are going to be finding their rank somewhere in that range of the, what color is it coming? Blue. Okay. If I can merge these two, I'm done. So for every block of blue on the top list, I'm going to find the corresponding block of blue in the bottom list and merge them. But this bottom list can be too big. If it is too big and I want to, then I have to do something smart to merge lists. Otherwise, I can. If it were too small, or rather, if it were small, nothing is too small. If it were small, say log n sized, then I could merge that list with this list sequentially in log n time. Right? Unfortunately, this is not small enough for me. But if I look at one of the blocks within it, which is log n, it's definitely going to land somewhere between in that blue block, and we know exactly where, right?
So here are we using the old blocks again?
There is no new block.
In the sense, sir, we had made blocks in the lower full array of log n sizes, right? So are we using the same
blocks? Yeah, log n sizes.
New blocks in
no point. No point.
But the endpoints of only those blocks are.
Right.
And the position of the endpoints of the older blocks is only known in the upper array.
Right. That is already.
What we want to know is this purple, is it? Purple block is going to fall where in the other list? If we know where the endpoints of the purple block fall, then we are done, right? And the endpoints were selected in this dot list. We know their ranks, right? And definitely their ranks are going to come in that cyan space, because that cyan and this purple, or the bigger blue, it's cyan here, bigger blue and the smaller blue at the top are going to merge with each other. We know that. We just have to figure out which parts of this bigger blue merge with which parts of the smaller blue, which can easily be figured out by going in the backward direction, because we know where the purple will want to go, right? It's going to be one part of that bigger blue. Now we are guaranteed that every pair of merges has at most log n elements. Right? If it turns out to be perfectly balanced, it's log n on both sides. Otherwise, it's log n on one side and smaller than log n on the other side. Right? So each merge can be done in log n time. How many such merges are there? N by log n, right? In the worst case, twice n by log n. That many there, that many here. And work done? N by log n independent units of work being done, each being done in log n time. So log n times n by log n is order n.
So this part I am not clear about. Why are there twice again here? Twice such log n's to be merged?
Because whenever we are merging, either one of the blocks from this fellow is being used or one of the blocks from that fellow is being used.
One of the log n blocks?
Yes, original blocks. Right? So every merge has one of these. Some merges may have two of these, but at least every merge has one of these.
If
they have two, then it's going to be slightly less. Okay?
So why do you find the dotted line back or dotted position?
Why? So that we can figure out where the purple should go. We can take the two endpoints of the purple, know where they land in the blue block at the top.
But you drew the dotted line before you drew the purple thing.
Yeah, so in the beginning you do both because you don't know what you're going to need. You can postpone it if you want to. Okay?
So we find it for all.
You find it for all. Yes. Any questions?
Can you find the rank of the elements in the lower list respect to the elements in the upper list?
First, we found the rank of the elements in the dot list, in the other dot list. And then, because we knew where the dot list came from, we can find the rank with a little bit extra work of all the dot list in the full list.
In the full list, the full list is the upper full list.
Both. Right? We can find the rank of all the upper dots in the lower full list and all the lower dots in the upper full list.
So what would be the final rank?
Final rank is what we are interested in, is the rank of every element in the top full list in the top bottom list, and eventually we are going to add it to its rank in its list, which is its position in its list. And similarly, for all the elements in the bottom list, we want to find their respective ranks in the top list. So we've broken it into 3 steps essentially.
I mean, that's clear on how you get to the last one. I mean, this is fine. Figure out the ranks in each of them. And you comparing the bottom with the top. So how are you getting the merge with the C? How is that rank?
So every of these blocks is bounded by two elements in the dot list. Right? So if you want to know where this block should merge, what it should merge with, you figure out where they lie in the other big list.
I mean, the big list is being not wrong here.
Big list is what is listed at the top and the bottom. If you don't think big list is drawn, then you have completely not understood what I have just said.
I thought if you take A and B and then you take...
Those, where we started with A and B.
I mean, A and top and B and bottom.
Doesn't matter. In the previous example, we had B at the top. So you can call B at the top here. Symmetric, so it doesn't matter.
But later, they have been expanded to the entire.
Right. After you merge it, now that step I'm not talking about, which is once you know your rank in the other list, you know your rank in your own list, you add those two and you put yourself at that position in this, let's say, C array. Okay.
So after this dot step, actually both of them expand
to become C. Yes, that's the bigger size. Okay. Convex hull. This is another example of divide and conquer. And I'm going to go very quickly through the trivial parts. Essentially, we are computing the upper hull only. Lower hull will be computed similarly and just connected to the upper hull. So focusing on the upper hull, and that is what is being done by divide and conquer. So we'll divide it into 2 halves based on their x coordinates, and then compute the upper hull of left, my left, doesn't matter what way you think, upper hull of the other side, and then find the common tangent, right? So something like that. The red is upper hull of one half, the other red is the upper hull of the other half, and then the green is the upper tangent. That's the main part of this algorithm, right? Which is what I'm going to talk about. But once you have found the green, what is the combined upper hull? Everything on the other side from the tangent side, right? Meaning the divider line side of both the hulls. If you didn't understand what I said, you didn't understand what I said earlier also. Why didn't you raise that question then? Isn't it obvious what you would do with the upper tangent to find the 2 hulls? If you understand what the hulls are. Do you understand what the hulls are?
2 upper hulls of the 2 sides.
Yes.
we want to merge them to get the
the upper hull of everything.
Right.
So once I've drawn the tangent, what is the upper hull of everything?
The connecting points.
Suppose we say that both the hulls are always computed in clockwise direction. Okay, so we are given the clockwise hull of left side, clockwise hull of right side, and I want to generate the clockwise hull of the result. What needs to be done? If I tell you that the 2 points on the 2 hulls where the tangents meet, so let me be more precise. We've got A0, A1, A2, A3 all the way up to AN, let's say, and B0, B1, B2, B3 all the way up to Bn. Okay, and I say I is the tangent point on one side, on the left side. J is the tangent point on the right side. What is the resulting hull? Exactly, A0 up to AI, then the reverse of Bj up to Bn. Okay, because wait, not reverse, that's also in the same direction.
BJ to BN.
Just Bj to Bn. Okay, now the only thing that remains to be done is where do I get these I and J from? And can somebody remind the rest of us?
Do a binary search.
The class area.
We should start with point and we find for each point you find whether it's a tangent.
So we can.
So you find a tangent by doing a binary search from each point to the other point of the
So trivially, we thought you can do is choose any 2 points, one here, one there, and then connect them and see the cross products.
Right, so I've got 2 hulls and I don't know the real ij, I'm taking 2 candidates, any candidate on the left side, any candidate on the right side. I would typically take the midpoint, right, because I want to do some kind of a binary search. Now suppose I fix j, okay. When can I tell if I is the tangent of the other hull from j, of this hull?
The size of cross products are the same for all rest of the points.
You really did want to do cross product? This is 2D.
You use a direction.
Just angles.
See the next point and the previous point, the line is same.
So if you look at the 2 points on the 2 sides, if they both lie below the line, then you've got the tangent.
How do you figure out that they are aligned?
Below the line?
By putting in the equation and seeing the.
Right. Okay. Now, suppose they are not the tangent, as in this case.
Suppose there is no.
No, suppose I that I chose was not the tangent because 2 points were on the opposite sides. Which way should I move? Is the tangent on that side or on this side? Why? What is that condition that says it's on the right side? What if I were drawing a line to this other line, other point?
Point should be below j, the tangent.
Sorry?
I mean the other hull, all the points should be below j.
So one is left, one is right. We don't need the angle. We just need to know which is below and which is above. And we know that it's going from left to right, clockwise.
So basically the slope should increase.
We just need to see, so one is up, one is down, right? As we go from left to right, are we going from down to up or up to down? If you're going from down to up, then we need to move further up, right? So all the left points from I can be discarded. Tangent cannot be there. Similarly, if I'm on the other side, then all the right points can be discarded and you only concentrate on the left side. So at each step, you can discard half the points and keep narrowing it down until you have found the tangent. Okay, so I found the tangent from J. This is not the upper tangent, because I had chosen the midpoint of the other side.
Please repeat, how did you choose which point you used?
We started, so in the beginning we chose the midpoint of both sides. We connected them. We put one as an anchor arbitrarily, right? And we said, let's find the tangent on the other side. And we found it after log n steps. Okay. Now we are interested in finding the full tangent. Do you think the point that we found on the other side is a point on the final tangent?
No, may not be.
It may be, it may not be. Right? So we could find the tangent from here, which is what ultimately you'll end up doing. But that need not be the tangent. However, from this other point, you can find the tangent to the other side and keep doing this. The analysis gets a little complicated, so I skipped through the analysis part. It can still be done in log n time, because each time you're reducing your set to enough. But you can see this intuitively in the following way. Let's give this a name. The point is K. The real tangent of the other hull is T. If I draw a line from the found K to the chosen point J, can we tell which way the real tangent is? It's exactly by the same rule. Okay, and hence not tangent from only that point K, but the real tangent also has the same principle. Right? At any stage, that's for analysis part, the intuition for the analysis. At any stage, you can tell that the real tangent is not in this half.
Because the way we choose our half does not depend upon the point from which the line is visible.
Yes.
It's just the point where it is.
Right. Okay. So, without going into the intricacy of the analysis, the algorithm is only this. You choose a point on one side, search for the tangent from that point, keep that point and search for the tangent from this point over here. Keep this point, search for the tangent to that point here. At some point, you will converge to the real tangent. Okay, after a small enough number of steps.
And then it may start oscillating. Is it possible?
No.
What is the checking condition for the final tangent?
Yeah, tell me.
Both the points on this, both C1 and T2 are the 2 points,
And both their neighbors on both sides are below it. Now let's move on to this other algorithm that we were discussing the last time, which was to find the minimum of n numbers. Okay, and that belongs to the class of accelerated cascading. And I had told you that we have seen one example of it just now, where we took one fast algorithm and not so optimal, and another optimal algorithm not so fast, and combined it by setting the right size of the input, right? Sampling the input in some way, or turning it into blocks. And we're going to do something similar. But to begin with, we are going to find it's almost trivial to find an order 1 min finding algorithm. We can find an order log n min finding algorithm using the balanced binary tree technique, which will take optimal time, optimal work, but not a satisfactory time. Okay. Just for reminding, how does the order 1 algorithm work? If I have n squared processors So n processors are comparing the element I to all the n other elements, right? N minus 1 processors. I'm not going to worry about the boundary condition. And what do they do?
Any of the element is bigger than this element, then they set a flag.
If any of the element is bigger than this element, then set a flag. For what? Set whose flag?
My own one flag, I have a flag.
I's flag.
I's flag.
It's the same thing. Whoever is the bigger, who's that guy's flag? You said if I is bigger, then set I's flag, which is the same thing as saying if J is bigger, set J's flag. Okay? So for every win, somebody is setting M3's flag, where 3 is being compared with all the other things. Right? If 3 didn't win any of the battles, then nobody is setting 3's flag to 1. But if 3 is winning many battles, then multiple people are setting 3's flag to 1. So it requires concurrent write. Okay? But what kind of concurrent write? Anything. I just need one of those ones to succeed. If it's common, they are always writing the same thing. If it is random, anybody's one will get written. If it is priority, one of the ones will get written based on the priority, right? So it doesn't matter which CRCW we have. And then, who's the winner? Who's the min now? Who didn't win any? There is only exactly one which didn't win any of the battles, which is the min. Right? So everybody checks the n flags that we have generated, and one of them will say it's still 0. Nobody wrote a 1 here, and that is the min. Okay? And there is no concurrent thing necessary there.
If they are non-unique numbers, then
If they are non-unique, then you have to do some further. If you don't want concurrent over here, then you have to do some further breaking tie over there. But right now it doesn't matter.
So it's still a common right.
Sorry?
It's still a common right.
It will still be a common write. Okay? So we've got a fast but less than optimal, right? Order 1 algorithm, really bad work. Order n squared work. If we were trying to implement it with p processors, we would expect to spend n squared over p time. Right? Versus the simpler algorithm, well, simpler or not, the default algorithm, which we have studied about earlier, where it was order n work, n over p time is all that would be needed, right, if I had p processors. So can we now make the domains of a certain size such that we can keep the cost, the time, maybe as good as constant, maybe increase it slightly, but reduce the work. Here you will see that the same kind of technique we applied to merge such two algorithms in the case of merging will need to be applied again and again, because we're really far from the optimal cost, n squared versus n. There we were at n log n versus n, right? So we'll have to repeat it a few times. Okay, so let me stop. Basically, at a high level, this is what accelerated cascading is about. You try to, instead of in the basic binary search, binary tree type technique, you break it into 2 elements at a time, right? You say, I'll take pairs, then I'll take pairs of pairs, meaning the results of the pairs. And so each time I'm going to reduce the number of elements remaining by 2, and at the end the winner will win out. Which is basically the same for all balanced binary tree techniques. If you want to make it faster, you would essentially intuitively do what? You will increase the branching factor. Right? Instead of somehow only saying find the min of two things, you'd want to say find min of many things. And so the tree will get stunted. That would be the idea. Right? And that's the idea of the accelerated cascading technique.
How does that decrease the work? So we are trying to decrease time.
Yes, it will decrease time and hopefully not increase work too much. It might increase work because it's in two you are using one processor. Now if you're making blocks of bigger size, you probably are using more processors. Okay, and the general idea, this is not always square root, but in order to branch out faster, either you'll have instead of 2 children at the root, log n children at the root, or root n children at the root, things of that sort. And then each one of them may have root of its size children, for example, and so on. So let's see how that would work. If I break the list into root n size blocks, root n of them, what can we do with it?
So we can use the previous algorithm and
You can
get
pick
the
the
minimum
root
of each block and then.
So if we apply the previous algorithm on each of these blocks, how long would it take on each of the blocks? Order 1 time, order n work, right? Because root n is the size, square of root n is the work, and which is n. What is the total amount of work? N root n, right? N in each of the blocks, root n such blocks, total amount of work will be n root n, right? And then we have root n minimas now. We have one more step to do. Still root n size. One more step. Order n more work. So total order n work, n root n work, we have, and 2 steps. We have figured out, before we extend it, why root n? Could we have tried log n or things of that sort?
So root n equal to n. Root n square equal to n because we had an n square algorithm.
It won't decrease, right? There's too many of them. If we make log n, then we still have too many blocks left. Okay, so root n is balancing on both sides here, because once you find the minima, there is a small number of them, and to find the minima, you had a small enough number to find the minima of. Okay, suppose we still break the list into root n things, root n sized each, and instead of applying the original algorithm, we applied the n root n algorithm on it. So instead of taking the square of the number of processors, it takes number of processors times root of the number of processors. So what's going to happen? We have root n times, what is n root n of root n?
Root n into root n.
N raised to what?
1 by 2 3 by 4.
3 by 4.
9 by 4? 3 by 4? So the entire thing, there are root n things, each of size root n, and on that root n size thing, we are applying the previous algorithm. So this is root n, root n, times root n. Right? There are root n of them.
Okay, you want the whole?
Yes, I do want the whole. So it is what?
5
root n, root n, root n, right? And the time is what? Order 1 is the wrong thing to say. It has gone up slightly. Still order 1, right? Still order 1. We can keep going. Then it won't be order 1.
Won't that be like an infinite sequence?
At some point, when you take root n, it still is the same number, right? You get down to 2, so now divide it into root n. So 1.4 and 1.4, you can do that, right? So you'll divide it into 1 and 1. Then say, now take root n, divide, it remains there, right? So there will be a leaf level somewhere. So if you just think order 1 time, that won't work, right? Because this is dependent on n. And if you look at the series, what is it? N 1 plus 1, n raised to the 1 plus 1, n raised to the 1 plus half, n raised to the 1 plus 1/4, 1 plus 1/8, 1 plus 1/16. So the series is n raised to 1 plus 1 over 2 to some I after I levels. And I says how many steps. Right? So if the work is 1n raised to the power 1 plus 1 over 2 to the I, then you have taken I steps. And we would like n raised to 1 plus 1 over 2 to the I to be around 1, right, at the leaf level. So what is I?
Log n should not be there.
Do it on a piece of paper. Log of n? K. What is K?
So if you want to reach to n raised to k,
I can't reach to any n raised to k, right? Take it to the logical conclusion where leaves become size 1 or so, greater than 1. So it's log n. The total number of levels will be log n, and n will be working every single time, so it's n log n work. That does it should have come earlier. So n raised to the power 1 over 2 to the I should reach 1, right? Or greater than 1.
So that won't be solved.
For that I come to
For that I comes to infinity, so that we can
Greater than 1, right? Yeah, greater than 1. Some constant number. Fixed number. So it's n 1 over 2 to the I is order 1.
I need log n.
Agree? Log n? Okay, so just quick review. A fast constant time algorithm, but not nearly optimal, combined with an optimal, not a very fast algorithm. Essentially by extending the branching factor of the log n style algorithm. Okay, and it's important to note that the degree keeps going down, right, as you go down the levels of the tree, because the number of things, amount of work you're doing in any given node keeps going down as you go down the level of the tree. So the branch is also dependent on the size of the work that you're going to be doing. So now you've changed it from a constant branching level tree to a branching level that says something about what the size of the work to be done at that level is. And so at a high level, it's solved recursively, which is true for most interesting algorithms, although you may not necessarily implement it that way. And you do, for a small enough size of the problem, you do the non-optimal version, the basic version, the complete tree type version. And once it becomes big enough chunks, then you start repeating the fast algorithm. Okay.
Start top down.
Same. So you can think of it top down or bottom up. Typically, if you're going to implement it non-recursively, you do tend to start bottom. Again, that's not necessary.
I was looking at recursive.
Okay. I said that although you design and think recursively, you don't necessarily implement it recursively. Okay. And typically you'll get something like log timing. Okay. Let's go through one more technique and then I want to switch to CUDA because that's what you are going to be doing next. Let me, this technique is called recursive doubling, sometimes also called pointer jumping. Question.
We still got work of n log n.
Why did we get that?
We still got but the optimal is n.
Yes.
Right. Not reach. There's no technique.
Not this way. There may be a completely new way to do things, but if you're combining those, you're not going to be able to get the best of both necessarily without losing anything. Okay. So either you're going to end up making the fast one slightly slower, or you're going to end up making the work less than optimal. Sometimes you can get by with doing just one of them. At other times you may have to suffer at both places. Okay, here is one problem. In fact, before we look at this problem, suppose I've got a tree in memory with pointers, some n processes at our disposal, and I want to know the depth of each node in the tree, its path length to the root.
But you have only one point.
I have one what?
Just the starting point.
No, so everybody somehow knows their pointer. In fact, forget about everybody. I give you one node, ask you to find its depth in the tree. Which is a slightly more general version of the problem we are going to solve here, which is I've got a linked list, and I want to find your distance from the end of the linked list. How would you do it in a sequential case?
Ask the parent, start from the root, keep adding.
I want everybody's.
I ask my parent to which I am pointing, what's its distance, and I add one to it.
But
then that needs to have finished before I start.
That's two and right?
So
Right. So that fine. So give me the full algorithm. You'll start at the end, right? Because I give you the list, pointer to the list at the head.
Right.
You go to the end and you say, if I am just before the end,
n minus 1.
make me 1.
I start from the first. I call recursively my parent's function.
Okay.
I keep add one to it.
Okay. So you figure out the distance of your next and you add 1 to it. Right? And your next will similarly do something, add 1 to it. And that can't quite be parallelized, right?
This is
I
similar
can
to-
receive a message from the top, this count, and I add one and give it to my child, and then the process will do.
Still not.
So there are processors at each level.
Processors at each node.
At each node.
Okay. So you give the processor, each node a processor.
They receive something from above, add one to it and give it to.
How do you begin? What do they start doing?
So the root gives its one count to every processor.
Broadcast.
No, to the next level.
that becomes sequential.
Okay.
That is sequential.
No, one is not branches.
Order length of list.
Similar to the
List की बात है.
Similar to the
Should be similar to the prefix of
prefix sum. It's very similar to prefix sum. Okay. But because of the pointers, you can do slightly differently. You can do prefix sum also. But you have to kind of know, maybe if it's an array, then it's a prefix sum. But that idea, can it work? That broadcast type idea, where Suppose I just want to tell you what is my distance from you. I tell my neighbors my distance is 1 from you. In the meantime, they have been telling their neighbors that their distance is 1. Now that I have established that I am at distance 1, how can the neighbors update who were at distance 1 to become at distance 2? Suppose I am I'm going to use the next as a temporary variable. Imagine copying it, and everybody is simply figuring out the distance that's 2 units away. Right? Just figure out what is your distance. Something that's 2 units away. And then the next time. Right? But because the next has already done the same thing you are doing, it's 4 units away now. Right? So after log n times, you're directly connected to the root. Okay, so the algorithm is really simple. You initialize a copy of next. If next I is equal to null, then you say my rank is 0. Otherwise, my rank is 1. And then log n times, you will keep pointer doubling. Okay, so for all I, you say if next is not equal to null, then my rank is previous rank plus the rank that the next fellow has got, and then update the pointer to whatever next he had discovered. Okay. After log n times, you will have essentially reached root and got your rank updated. Same thing in the case of tree. If you want to reach the root, everybody is trying to reach the root, essentially figure out the distance to the root. You reach to the next, your parent, at the same time that guy is reaching to, or parent's parent you already had, that was the initialization. You reach parent's parent, that same time that parent's parent has reached its grandparent, so the next time you have reached grandparent's grandparent. Okay? So in log n times, n being your distance from the end, you will have reached the end. Okay. I'm going to break this here. We have many more techniques as well as specific algorithms that we are going to talk about. But I want to switch to CUDA because you're going to be doing that next. And I want to give you just a brief review of the architecture and then talk about the programming model. Any questions? Okay, let's stop here.